Good morning. My name is Ashley Damiano. I'm a student at UNC Charlotte. And thank you very much for having me today. I'm going to talk to you about a tool that was conceived by myself and along with professors Chris Beorkrem and Jefferson Ellinger at UNC Charlotte. The intent of the tool is to analyze conceptual massing with respect to collection of wind-driven rain, based on the premise that water is a very valuable resource that we tend to take for granted, and traditional means of collection only consider typically the rooftop surfaces of buildings, whereas high-rises and the collection on the facades of high-rises could have a significant increase to that amount of rainwater that could be collected. So why does this matter? Globally, 10% of the population lacks access to safe water. A third of the people in the world lack access to a toilet. A third of all schools lack access to safe water and adequate sanitation. And MIT researchers predict that in about 33 years, over half the population will live in water-stressed areas. Also, as areas begin to become highly developed, a lot of the surfaces are made up of impervious surfaces, which is causing urban runoff. And as urban runoff picks up pollutants, such as dirt, oils, fertilizers, bacteria, it's bringing those into our stormwater systems, our soil, our streams, ponds, oceans, contaminating drinking water, killing off wildlife and vegetation. And during a storm event, storm runoff is moving too rapidly to absorb into the soils, which is causing a lot of wells to dry up and the need for those wells to be lowered in order to access water. So current design standards take solely the horizontal surfaces of a site, so typically the roof and the surrounding property, into consideration when calculating for rainwater collection systems. However, 90% of the water that is consumed in a typical office building is used for non-potable uses, gray water consumption. So if we were to add the vertical surfaces of a high-rise into that calculation, that has the potential to very significantly increase the amount of rainwater that could be collected and reused, starting to mitigate some of those social and environmental issues that I just mentioned. So just to point out how much water we use typically, the average office employee uses about 7.8 gallons a day to flush the toilet, between 2 and 3 times a day. If we start adding that up in an office building that has around 4,000 employees, that adds up to over 6 million gallons of water used a year just to flush toilets. So you can imagine how much other gray water consumption there is in these office buildings. So once again, just to reiterate, if we were to start collecting the water on the vertical surfaces of high-rise buildings, we could increase that collection potential, increase the amount of water that could be reused, and start to mitigate those environmental and social water issues. So we were looking specifically at wind-driven rain, which is rain that is propelled horizontally by wind, causing that rain to fall at an oblique angle and intersect with the vertical surface. There's quite an extensive amount of research on wind-driven rain, about over 80 years of research. In regard to building science, there's a large number of parameters and variability that makes wind-driven rain very difficult to calculate and quantify. However, real-life measurements of wind-driven rain indicate that the intensity of wind-driven rain increases proportionally with the wind speed and the rainfall intensity. And that proportional relationship has been presumed in research over the past 60 years. So that became the basis of our calculations. Hofstad derived an equation to relate those proportions together, and that is what we based our calculations off of for this tool. So CACTOS is a tool that is intended to create comparisons between building masses and their orientation on a particular site using weather data from that site. So just as an example, on a 100 foot by 200 foot office tower, that's roughly about 30.5 meters by almost 61 meters. And 1 inch of precipitation at 5 miles an hour, if there was a 5 mile an hour wind, adding the vertical surfaces to that calculation increases the collection potential by 132%. If that wind was blowing at 10 miles an hour or 16 kilometers an hour, that nearly triples the amount of collection that could occur than just on the roof surface. So we began by importing weather data and stripping it down just to include wind speed, wind direction, and precipitation amounts over the course of 4 years. We further removed the days without any precipitation, any measurable rainfall, to make our calculations more accurate based on the wind speed and direction of that particular location, and average that out over the course of 1 year. That weather data is imported into Dynamo along with a Revit geometry conceptual mass. And then a grid of points is created in Dynamo, each point representing a certain amount of rainwater based on how dense that grid is and how large it is, and that is all controlled by the user in the Dynamo interface. Those points then are projected as rays onto the mass, which is based on the wind speed and direction from the data. And where those intersections occur, they are added up over the course of a year in order to calculate the annual collection potential on the vertical facades. Then the mass is reoriented on the site, also user controlled by how many orientations it cycles through, depending on how accurate you're trying to get with this. And then it exports the optimal orientation of the site back into Revit. So you have 2 orientations to compare in Revit. And you start to get results like this, where in this example, just adding the vertical surfaces in the original orientation increases the collection amount by 100%, and then reorienting it increases that potential slightly, about 5%. We use this just as a verification in the orientation. Obviously, a cylinder would collect the same amount no matter which way it's oriented. And then this form, you can see that adding the vertical surfaces to this calculation really increases the amount, whereas reorienting it on the site doesn't do a whole lot. Whereas the orientation of this building is pretty important along with the vertical surfaces. And then again, the vertical surfaces really increase the collection amount, and the orientation has kind of a slight effect on how much could be collected. Whereas this building has more horizontal surfaces, and so probably a rooftop collection system would be ideal for this form. And then again, the orientation of this building is minimal, but the vertical surfaces play a larger part in that. This tool further traces the way that the water would flow over a building using a sphere mapping technique. I'll play that again. So a sphere is created at the intersection of those points with the mass, and a line is drawn from the center to the nearest intersection of that sphere with the form, and then that point becomes the next center of the next sphere, and that traces the paths down the mass. So here's a little video demo of how the tool works. You're importing the weather data here, and this is kind of what it looks like. It's pretty basic: wind speed, wind direction, and precipitation. This is where you're able to control the grid of points that are projected onto the building the size and the density. And then this is where you would select the building form in Revit and control the orientation variations. And this is the result that you get. You can see kind of the original form that has been turned off, and then this is the reoriented form. Start to see the total number of points that are intersected with each face, each orientation. And the amount collected calculated up to an annual total for the original orientation and the reorientation, as well as on each surface. And then this is turning on those paths of the points down the down the form of the building. So the purpose of that final part is to indicate to users where collection might happen before the water hits the ground. The reason being that could reduce runoff and also reduce the amount of energy required to pump stored water back up through the building for reuse. It challenges designers to take the way that water flows over the form into consideration early on in design, kind of in the schematic phases, rather than using it as a solution later down the road. So we imagine this as a series of integrated tools for the evaluation of multiple performance criteria, such as CACTOS or fog collection or solar radiation, daylighting controls, just different ways to evaluate a building, and using tools like that with one another to create a successful building, to create more resilient neighborhoods. Cities like New York and other large cities could respond better to stormwater events rather than just shedding the wind-driven rain and creating more urban runoff. Situations like the Haitian earthquake back in 2010, where conditions were really exacerbated by the lack of access to safe water. If there were a nearby town or somewhere in Haiti that wasn't affected that had such a system or such a collection system that they could give access to safe water, maybe those conditions would have been a little bit less disastrous. The reuse of the water could also be used in irrigation, fire protection, gray water consumption, such as the toilet flushing, heating or cooling systems, or could also be integrated into the envelope designs by using it as a cooling system for the envelope or creating light shelves to disperse or control daylighting. One example is the Center for Architecture, Science, and Ecology at RPI has developed a modular facade system. It's a series of glass blocks that diffuse the sunlight. Gray water flows through channels within each of these blocks embedded in the surface, and the solar radiation is utilized to sanitize this, the gray water that's flowing through, or to purify, so that it could be reused and also be part of the facade system. So to conclude, we wanted to create an integrated method to analyze and compare massing studies against one another. Also to challenge the current design standards in the way that rainwater collection is calculated on high-rise buildings. And also, as the need for water in urban areas increases, tools like CACTOS will provide designers with the ability to integrate rainwater collection into the primary schematic condition for successful building design. And you can contact any of us if you have questions or comments or would like more information.